I will begin with a word of prayer. Yeah. Dear Heavenly Father, we thank you for this day. Again, I thank you for these students. Just ask you to bless this week. Help us to glorify you what we do. And just help the students to continue preparing for their test too, just to do their best, Lord, tomorrow for your glory, Lord. In your name I pray, Lord Jesus. Amen. Excuse me. So let me just address the 3 big errors I saw in the math battle. I think these are the 3. Maybe there's just 2. Come to me as I'm talking to you guys. But first of all, if I have something like, the limit as xy goes to x naught, y naught, whatever that is, right? And I've got some function of x and y here, right? And then I get that, if I do, the limit as, xy goes to x naught, y naught, f of xy along, let's say, r of t, let me see here. Let me just let me not use a bunch of language. Let me just kind of describe what you're doing less precisely. Let me just say, and you have this, right? And then what I've seen on not just one team, but a couple teams, where they look at path limit, and they get 3, and they look at path limit 2, and they get 3, right? And then they're like, oh, so the limit exists and it's 3. No, this you cannot do. The only way to prove a limit exists is either through a squeeze theorem argument, through direct algebra, or by change to polar coordinates, as far as I know. Those are the 3 ways to show a limit, a 2-variable limit exists. Path limits just get you non-existence. They don't get you existence, because you can't take enough paths. Even if all possible linear paths converge and give you the same answer, it still doesn't prove that it's equal. Yeah?
You can generalize a generic polynomial function as a path, and you can prove it for that.
Nope. Even that wouldn't do it, I don't believe. I mean, anyway, if that's going to do it, you have to prove it to me first. That might be enough. Arbitrary polynomials, that might be enough. But we've already seen that, there are examples where all linear paths go to the same thing, all quadratic paths go to the same thing, and that when you get to cubic, all of a sudden there's a difference. So it's nasty. You have to either change. So the way to do the problem in the math battle, if I have it open, which I may not, watch, I haven't opened the one thing I want to talk about, probably. So if I can find it. Come on. So the way to do this one was just to change to polar coordinates. And I think maybe 2 teams did this. There's a larger point here, which is really less about your tests and just more about strategy. If you're working on a team and you have time and you have 3 people, there ought to be at least 2 people doing every problem so that you can check answers. Because I had some teams that submitted answers that were just wrong. But they weren't wrong on the basis of total misunderstanding. It was a careless mistake. If 2 people had done the problem, then that wouldn't have happened. Anyway, that's kind of a side issue. Does this make sense? So we just changed to x. Since we're looking at the limit goes to 0, we can do this. Now I will say that this trick really pretty much is specialized for limits at 0, right? If I had a limit somewhere else, I would either need to create a new system of coordinates which made this kind of substitution plausible with respect to a shifted system of polar coordinates or something. That would be kind of a next level problem though. Anyway, so the point is here, this right here. Now one of you in this part ended up with a naked cosine theta, sine theta in the thing, and you're just well, it's 0. No. If you've got sine theta, cosine theta just sitting there, that goes to all possible values, like tons of different values as you choose different angles. That doesn't go to 0. The only reason this goes to 0 is because there's an r here. This r here allows me to ignore it. If not for this r, I'd be like, nope, limit doesn't exist, and then I could choose 2 different path limits to be sure about it. Of course, in the polar formalism, you can choose 2 different path limits by simply saying, I'm going to look at theta equals to, say, pi over 4, and theta equals to pi over 2 or something, you know? But okay, so that's one thing. The other thing, if I can remember, this is it's a major complaint, but also a minor complaint. It's a major complaint in that it just shows me you don't quite know what you're doing. It's a minor complaint in that it's really easy to fix. So like some people basically have told me this alone is the tangent plane. All right, but this alone is not the tangent plane. That's just an expression which is floating there doing whatever, I don't know. When it becomes equal to 0, then the solution set to that, that's the tangent plane. Right? So that little equals to 0 in context really, really matters because it's the difference between thinking you're understanding what you're doing versus you're just kind of like mimicking what I'm doing. There's a difference. So equals to 0, that's the equation of a tangent plane. I think one group forgot to divide by 3 here. That's the kind of thing that I would hope if 2 people were working the problem, it wouldn't have happened, right? Another group, I think, managed to miss the z squared term in the derivative. Like, I think you missed this guy sitting out here, which adds 2 plus 4 gives you 6 here, but you guys had a 2, one of the groups. I can't remember which one. Oh, I'm a dummy. Let me go on here, make sure there's time for your questions. Let's see here, what else? This one was impossible. The reason for that, I suppose there's different ways to see it, but essentially this, once I tell you that the motion is along this surface with the equation x squared plus 4y squared plus y is equal to 11, that means that you are stuck with certain relations between the rates of the change of x, y, and z, right? It's a related rates thing. But in particular, you're saddled with this equation that relates to the x, y, and z velocities. So that means I can solve for z dot in terms of the other ones, and that gives me z dot's minus 1. But on the other hand, I'm given x dot and y dot, so I can plug it back into the formula for speed, and I get square root of 2, which of course is not 20. So these are incompatible. The data is incompatible. All right. This one here, I think a lot of people, I think everybody, not sure everybody, but I think a good number if you got 7 right. So for the test, right, if I give you a surface, if it's parametrized, and you want to find the tangent plane, what do? You calculate the partial velocities, and then you take the cross product of those. That gives you the normal vector field, right? On the other hand, if the surface is described as a level equation, right, as a level surface, how do you find the tangent, the normal field then? Well, you just take the 3-dimensional gradient, right? So we have these 2 viewpoints competing. Now, problem 8, I think this is the thing most people are most shaky on at the moment because it's the last thing we covered, right? But let me just talk about the way to think through that. So here, you're given, see this, all right, so you're asked, the question asks you to find partial derivatives of z and w with respect to x and y, right? So what that means is your dependent variables in this problem are w and z. So since the dependent variables are w and z, this equation right here is huge. It already answers 2 of the questions. See, because from this I can immediately read off that partial w partial x is x, and partial w partial y is y squared plus 1. All right, I can see that because if I take x and y to be independent variables, if I look at this, I set dy equal to 0, that gives me partial w partial x. I set dx equal to 0, that gives me partial w partial y. According to the definitions that were laid down in the notes and the calculations we've done in here, right? Now, this is more annoying, right? Because it's got the dependent variable's differential dw and the dependent variable dz's differential, right? So I have to either get rid of one of these or the other, but I don't really need to well, I already got dw over here, right? So I want to get rid of the dw. So what I do is I just plug this in over here, and then I've got an equation involving just dx, dy, and dz, which is what I'm after. So once I do that and I rearrange things, I solve for dz, I've got this, and then the coefficients are partial z, partial x, and partial z, partial y, like that. Now, of course, we've also worked at problems in class where you didn't have to do it this way, right? Where I gave you a formula for w, a formula for z, and they're kind of intertwangled, and then you can just partial differentiate it and substitute things in, right? Sort of implicit differentiation style. So, you know, there's another kind of problem like this which doesn't require you thinking at the level of differentials, but I wanted to force the issue on this problem, so that's what this was about. So, because you don't even have formulas for w and z, right? You just know that these differentials hold. I think most people got problem 9, but not everybody. It's okay. Like I said, well, no, not problem 9. My bad. I'm thinking about. I think everybody got problem 9. That's a pretty standard problem, right? This is the same as what vector field problem? Do you guys recognize that this is exactly the same question as f equals to y e to the minus x, excuse me, y plus e to the minus x, comma, x cosh y, x plus cosh y, right? And question mark, is this equal to the gradient of like a little f, right? The question that's asked here, solve that, and the question here, is there a function whose gradient is equal to that vector field? These are the same question, right? So there's a natural connection between those kind of vector fields and solving those so-called exact differential equations. Now, let us go on here. This here, so when you're explaining why something's not possible, you need to like not leave me halfway through a sentence or something. Like some solutions were, I feel like they were on the way to saying something, but they didn't quite say it. So just like come out and say it. Okay, so here, the issue is that it can't be possible to write it as the gradient of a little f because the mixed partials commute, and when you calculate this versus that, you get -1 versus 1. There may be other reasons, but that's the one I latched onto, all right? So, this here, I had one team give me a dot product, which was a vector. That's not good. Dot products are numbers, right, or functions in this case. So you have to add the dot product. It's not a vector. But anyway, I think this is an interesting example, right, because it gives you a window into how we can use the chain rule to solve problems which we didn't have answers for before in Calculus 1. Now, how did we do this in Calculus 1? Do you guys remember? Did anyone ask you to differentiate like x to the x or t to the t when you were in Calc 1? Do you remember what method you used? I asked my Calculus 1 class to differentiate x to the x. Use the what? No, we can't do that because it's got variability in the base and the exponent. So it's not actually it's not an exponential function and it's not a power function. So neither of my chain rules really quite apply. It's kind of, yes, implicit differentiation is what we did. Like, we did this. We said y equals x to the x. And I say the we and the, you know, I don't know which we we're talking about here, but anyway, you got my idea. Natural log of y is natural log of x to the x. Like this is how we did this back in Calc 1. So this is just a new take on an old calculation, right? You can also understand how to calculate such derivatives by applying a chain rule to a multivariate function. Okay, and then, well, anyway, I think we talked about 12 enough this last week already. But all right, with that, any questions about anything in here particular? We can go back to the. I will say this: I kind of soured on. I think you guys are mostly right about the direction of the gradient vectors with respect to the level curve, so that's great, mostly perfect. I think one of you. One team wanted there to be one where it didn't exist, so like B is close to the place where it doesn't exist, but it's not quite there yet, right? The center point is where the gradient is 0, so you can't really draw it. That's a critical point. We'll be talking a lot more about critical points after the test, and that's not some sort of joke about your grade. There's actually something called a critical point in here. I'm sorry, is it too soon? But you haven't taken the test yet. What am I talking about? Everyone's going to get 100. Woohoo! Wait a minute, no. How many points did I put on a test? Everyone's getting 120. Yes. All right, so I have a different number of points on the test in each class I'm teaching, so I don't remember.
Is that a promise?
What's that?
Is that a promise?
No, it's just illogical optimism on my part. But no, logical optimism, because you guys have done the work, and now you understand. Woo! Okay, so, I was just going to say, for this one, there was some good answers and there were some really, really lost answers. So some of you need to work on that. How do we do, what's the chain rule? Now, this is not written in stone. Like you could just as well have written like partial w, partial x here, partial w, partial y, partial w, partial z. And I'm sympathetic to people who wrote dx dt, dy dt, and dz dt is here as well. There's certainly room for different formulas. Can you guys tell me 5 different ways we write the chain rule in Calculus 1? So we have f composed with g prime of x is and that's the derivative of the composite, right? So one way to write that would be this, f prime of g of x times g prime of x, right? What's another way we write the chain rule? How about we also write this like df dx of g of x, right? Times dg dx, we write that. That's another thing we write. But yet another thing we write is df dg dx. Well, we don't write that too much. We typically write that more with like a u, right? When the u is the inside function. Like that. For u equal to g of x. Did I get to 5 yet? Oh well, I guess just 4. But these are all commonly used. Especially this means that you're taking the derivative of f and you're evaluating at g, or more explicitly here, right? Because the chain rule evaluates. Now, I did not take off points at all here for you not, and neither did my answer, express the truth that partial f partial x is where evaluated where? It's evaluated at this, right? And partial f partial y is evaluated at that mess. And partial f partial z is evaluated at this mess, right? So like I did not even quibble over that. That was not the point. Anyway. What I was going to say is I'm not super happy about these questions. They're my brothers. And like, the wording is not quite transparent enough to my tastes. Like, it begs, I feel like there are students who could have the right idea and get these ones wrong. And so I think what these are exploring is good, but I think the particular formatting of these questions I'm not super happy with. I'll just say that. As you can see, I chose yes and no for the one, I mean, I think actually the answer is affirmatively yes on this one. I just forgot to white out the no. See, when I wrote this, when I selected no, there was a reason for it, and I forgot what it was. But But anyway, the larger point here is this being continuous means it's continuously differentiable, and continuously differentiable implies differentiable. Continuous differentiability means that the partial derivatives are continuous. If the partial derivatives are continuous at the point, then all of my wacky counterexamples in the notes blow up. They're not applicable. However, existence of the partial derivatives alone does not imply differentiability, because the differentiability is like a multivariate limit kind of thing. So much like those path limits. So essentially the partial derivatives exist as kind of like path limits along the x and the y directions existing for the directional derivative, but you actually need all of the different directional derivatives in all directions existing, and you need them to be like nicely glued together in order to get the tangent plane existing. So yeah.
Due to the limited nature of the derivative in C, you have a point where there's a gap in the graph where you bridge the same slope coming up to that point. So the gradient would be continuous, but that point doesn't exist, so it's not continuous.
Well, I don't think so, because the if I have that this exists at that point, assuming that exists at the point, all right? But this is kind of my complaint. What you're talking about is people might think about these kinds of things. If this exists at the point, then we have a theorem that differentiable implies continuous. So like you can't have the function jumping. But anyway, the point of this really was just Chloro's theorem, honestly. But see, in order for that to be I mean, is it possible? See, you could have selected yes, I would still give you credit there. The only one I really can reliably take off points for is maybe this one. I don't know. I may have just taken off a point because you guys didn't give me any kind of explanation. But if you want that point back, you can argue with me. But I did round up everybody's score by a point, so it's probably already been addressed. Anyway, my point is, I'm sorry about these questions. Okay, I don't like them, the way they're formatted at the moment. All right, well, we're back where we started. Do you guys have questions? Let me look through the homework if you guys don't have questions. Let's take a walk down memory lane here. This was mission 3, right? So what did we talk about at the start of everything? Well, I forgot to talk about topology, I guess. Then I came back and talked about it the next day, right? So we talked about what is an open set, what's a boundary point. So we did talk about that. That could come up. Of course, there should be at least one limit problem on the test, right? I mean, that's an important topic in this course. Probably I have to ask too to make it interesting, right? There should be, to make the test most interesting with regard to limits, there ought to be one where you could either solve it by like, a substitution to polar coordinates or spherical coordinates. And then the other one where you need to look at 2 different paths and see that it doesn't exist, or who knows, maybe it could be just as simple as, hey, it's continuous, you plug in the point, right? Sometimes I do that. Of course, you need to be able to partial differentiate. Like, that's a big thing on the test, obviously. So if you're weak on some aspect of differentiation, you should definitely review. But I think most of you have, at this point, had your memories jogged about like quotient rule, chain rule, product rule, right? These things have happened. You've seen what you've forgotten, I think, a lot of you. Let's see here. Remember this kind of problem where we're given the value of the function defined everywhere by a formula, and then one point we get a number, a variable a, which we can pick whatever we want. We want to make the functions continuous, so we just need to choose an a that makes the value of the function at the origin like glued together continuously with the rest of the values. So there we figured out a was 1. There are other problems like this which are possible. Problem 34 was difficult. So, I could ask something like that on the test, but I would be trying to separate my A's from my B's with that question. It wouldn't be one I'd expect everybody gets right. But the analysis here is a little bit difficult. Essentially, the analysis really boils down to understanding when is the denominator 0, right? Because the denominator 0 is where the trouble comes from. And so it takes me some effort to analyze where that denominator could be 0. But that effort, honestly, is it calculus 3? Not really. What you're dealing with there is picky precalculus, truth be told. So, all right, as you can see, it goes on. Let's see here, what else I want to talk about. You guys remember the directional derivative, I think? So the directional derivative, this is a good problem, like problem 37 right here. Here's a relatively simple function of two variables. Given a point, you're supposed to find a unit vector which it changes at rate 12 and at rate 15 if possible, right? So I calculate the gradient, and then I calculate the magnitude of the gradient, right? And then what? So the magnitude of the gradient, plus or minus, gives you the maximum and minimum rates of change that are possible, that are even possible for the function at the point. So I can't get rate 15, like part B is impossible. I can't reach rate change 15 by taking the dot product of a length 13.15 vector with a unit vector. You just can't do that. And then part A, well, algebra, right? So I have the directional derivative is the gradient, which here is 13.2 dot with the unit vector AB. That gives me this equation. And I also know a squared plus b squared equals to 1, so then I can solve, substitute, solve the quadratic, and I get these two solutions. For a two-dimensional problem, there will always be two directions in this kind of problem that are answers. For a three-dimensional problem, you get a whole infinity of answers that are tracing out some sort of circle in ABC space or something. Any questions? You guys can jump in at any point. Okay.
Do you have our mission 3 graded?
Hey, that's a good question. I should have both. The grader said he could get them back. Howdy. And not bring back much. That's all I did. All right. Hooray. Well, I told your grader I needed these back to you guys today. And he does have mission 3 here. Mission 4, he said he'd get back to me. I thought he was going to bring them in this morning, like last time, you know. But apparently that has not happened yet. But yeah, your mission 3 is up here. Wonderful question. Thank you for asking that. I forget to check the file cabinet over there. Sometimes he just returns them there. There's probably an email waiting for me telling me about this sitting in the math department waiting for me to pick up. So, other questions while I am handing these back here. Ooh. I'm guessing from these scores that he's graded by completion, and he's picked a couple to grade because I see some fairly low scores here, which to me suggests that what's happened is you guys have kind of not done a super awesome job on a problem or two, and that's one of the ones he picked to grade. And then he used that like he probably used a score on a couple. If I had to guess, I'm going to say he's graded by completion. Do you guys know what I mean by that? So, I mean, I'm speculating. I don't have the in any event, the solution to mission 3 is right here. So if there's any problem you guys want to talk about, we can talk about it. Nobody? So which one did you guys get wrong you want to talk about?
Can we look at the bonus?
The bonus? I don't think I have a solution to bonus, actually.
I do. Apparently, we don't look at the next one.
I mean, for the bonus, you know, I would calculate the gradient of t, and then basically just look for where that gradient vector had a magnitude, which was less than like 0.1. So wherever the gradient is less than 0.1 would be a place where the Scout Ninja could detect, where the insects could detect him. So you'd be trying to solve where the magnitude of the gradient vector is less than 0.1. If that's what you did, then that's good.
I think so.
Okay.
I demonstrated the symmetry of the first and then just one insert.
Okay, that makes sense.
So I'm not sure.
Well, I've got a +1 on my like he gave one. Wait a minute, no, that's for 45. Never mind me. Well, I have to talk to your grader to, you know, he doesn't talk to me. I just give him the things and say you grade fairly, you know. So he's graded all you the same way, so it's fair. But so what's the theory? You have a theory on what he graded?
The ones that he wrote beside.
The ones that he wrote beside he graded. Yeah, that seems reasonable. Yeah. All right, well, hopefully I will get your mission 4 back today, since he said he would. And when I do, then I will, you know, make an announcement or something. You can come pick it up later, perhaps, ideally. I do have the solution to look at for mission 4 if you guys want to. Well, let's see, is there anything else in mission 3 that you, I mean, in terms of content, you know, forget about the scores for a second here. Is there anything in particular you want to talk about content-wise here? Nobody? All right. Let's see here. So we could look at problem 58 over here, I guess. You guys had some questions about that. Everybody get 13 times the UU derivative plus 10 times the mixed derivative plus 2 times the VV derivative for your Laplace equation. You guys get that? What's that? You don't remember? Ah. So this brings up a point of order. Going forward, it would be wise to scan your solution for the mission that's right before the test in the event that this happens again, right? So that you can look at your answers and compare. Let's see here. Let me go back to the start. So here, let me just talk about 57 for a minute. So here, I think, so my problem in some sense is unkind here, because I've asked you to calculate the gradient of r squared, and the gradient of 1 over r, right? A more friendly way to ask this question would actually have been to ask you to do what? Calculate the gradient of r squared first, right? Because notice that the gradient of r squared, in fact, by the chain rule for the gradient, is 2r times the gradient of r. So, there's a chain rule here, right? Like, in particular, if I have the gradient of a function, f composed with g, f of g, right? Now here, let me use notation. I'm trying to think what's the right best notation here. H, let's say h. H of f. All right, and so here, f is a function perhaps of x, y, and z, all right? Here h is just a function from the reals to the reals, okay? So if you look at that, what do you got? You've got partial x of what? Of h of f of x, y, z, right? Partial y of h of f, partial z of h composed with f. Well, how do you differentiate? How do you differentiate a composite? You've got a function of another function. Well, the chain rule there is, it's pretty simple actually. It's just h prime times the partial derivative. So like this one, it gives you h prime of f times partial x partial f. This one gives you h prime of f times partial y partial f. This one gives you h prime of f partial z partial f. And so there's a common h prime of f everywhere, right? And then what do you got? Like this, right? So that's h prime of f times the gradient nabla f. So anytime you're looking at taking the gradient of a function, so like this problem, my f of x, y, z, I'm saying is the square root of x squared plus y squared plus z squared. That's the pattern I'm seeing there, okay? Which I've called R for this problem, right? And okay, fine, it's n-dimensional, my bad. But this calculation generalizes to n dimensions, okay? So my point to you is if you know that, and I did try to get your attention about that in a previous homework exercise with the f and the g and the f squared equal to g or vice versa. You remember that problem? The point of that problem was to make you aware of this. And anyway, so this right here is super easy to calculate because r squared is just x1 squared plus x2 squared plus x3 squared, da da da, right? So taking the gradient of this is really, really simple. It's just polynomial. It's 2x1, comma 2x2, comma 2x3, comma da da da, 2xn. But on the other hand, the chain rule tells me this, so I can then just divide by 2r. The 2's cancel, and I derive that with much less calculation, actually. But I don't know. Like, you guys can differentiate a square root just the same, so whatever. Okay, so admittedly, I kind of have another workaround up here, right? Which was, I did what? Instead of, like square root, I'm like, I don't want to deal with square root, so I squared it. I took the total differential, right, and then I solved for dr. And if I do that, that's another way to calculate partial derivatives with respect to the variables in a nice way, right? Now, of course, you could just take your medicine and differentiate the square root function. That's also fine. But if you make use of some of these ideas, you can simplify your calculation considerably. Anyway, any questions about this one? No? I would like you to have on your formula card the formulas for the gradient in the cylindrical and the spherical coordinates, okay? So make sure they're on there, all right? Because I would like to be able to ask you like a simple question about calculate the gradient in polars or sphericals. You know, that's not a hard question if you have the formula. Now, if for some reason you forget the formula, you want to ask me, I might give that to you. But I'd prefer you just have it on your card, right? If I was to ask you a derivation question about one of these formulas, it would probably be the part that we'd actually done in class carefully. All right, which part did we derive in class carefully in terms of the gradient and other coordinate systems? Which one did we do? Do you remember?
The spherical.
We did spherical and polar. That's generous. I would say we did polar. Spherical, because we got hung up on the what? The unit vector and the phi direction, right? My phi hat was kind of, was off by a minus, right? So I would say the polar is the more likely one if I was to ask you to derive something. In other words, to derive, well, I don't have it in front of me, but anyway. Let's see here, and I would say finally, last but not least, don't forget about the, obviously be ready to find the equation to a tangent plane to a surface, right? Obviously there are going to be chain rule questions, so you got to know your chain rules. Remember that example we did on the board where we actually gave you numbers for the partial derivatives and asked you to put it together? That's a very common test question, something like that, where you don't have formulas, so you can't just plug stuff together and just regular differentiate, right? You have to go through the chain rule. I will force the issue. But anyway, that's pretty much all I have to say, so I'll just shut up. And if you disagree with your grading about mission 3, sorry about that. If mission 4 is also like this, then we'll have to do something, okay? Because I think some of you actually did a pretty good amount of work on this mission, and it seems your scores are a little bit lower than I'd like to see, which makes me think that the grading was a bit random. So anyway, sorry guys. See you tomorrow.